Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 8 today, Section 8.3 on graphing piecewise defined functions and shifting and reflecting graphs of functions. Objectives in this section are to graph piecewise defined functions, shift graphs vertically and horizontally, and finally reflect graphs. And this goes along with SLOC, construct graphs of inequalities, linear and nonlinear functions, and conic sections. So let's start with piecewise defined functions. My favorite example of a piecewise defined function I used to enjoy eating at Hometown Buffet, not so much lately. And they had a really interesting system at one time for determining the price for your lunch. If you are an adult, and of course by adult they mean 11 or older, sort of like the movies, lunch is $8.59, all you can eat, right? But if you bring the kids, they would charge 70 cents times their age. The idea being that a 2-year-old doesn't eat as much as a 10-year-old. So a 2-year-old would cost $1.40 because that's 70 cents times 2. A 10-year-old would cost $7, right? Almost as much as the 11-year-old, 70 cents times 10. All right, so what makes this a piecewise defined function, I am going to show you. All right, so a piecewise defined function means that the rule for what you do with the number that you're plugging into the function kind of depends on what range or interval the number comes from. So this is a really good example of that. So here's how it works. We'll say let x equal the person's age. All right, and then c of x, which is the cost of lunch, is going to be one of two things, or I should say determined in one of two ways. If you are an adult, 11 or older, then lunch is $8.59. I don't care if you're 11 or 60, I shouldn't say 66 because they did say there was a senior discount and I don't want to get into that. So we'll say, I don't care whether you're 11 or 55, lunch is $8.59. So C of 11 is $8.59, C of 55 is $8.59, C of 38 is $8.59. So that's if x is greater than or equal to 11. But if you're a child between 2 and 10, then I do care specifically what your age is. And what I'm going to do is multiply your age by 70 cents. So that's going to look like this. Okay, the cost of lunch is 70 cents times x, and that's if x is between 2 and, I'm going to write it like this. I'm going to write less than 11. Okay, so there's an assumption with this example that ages are only whole numbers. When we get into doing this for real, x can be any real number. All right, so I want to show it to you the way it's normally going to look. All right, so this is a piecewise defined function. C of x is equal to $8.59 if x is greater than or equal to 11, and is equal to 70 cents times x if x is between 2 and 11. All right, so now going back to the presentation. Oh, I'm sorry, I forgot to do I went ahead and did the problem without telling you what it was. So what we just did was we wrote a function for C of x, which is the cost of a lunch buffet for a person aged X years old, where X is between 2 and 65. Again, I didn't want to get into the senior discount. That would have given me a piecewise defined function which with 3 pieces, which is a thing. All right, but in this class, we focus on piecewise defined functions with just 2 pieces. All right, so our first sort of real example, we're going to graph the function f of x equals 3x if x is less than 0. but equals x plus 2 if x is greater than or equal to 0. Now, I want to give you a heads up that this is something that students find particularly difficult. I always get asked a lot of questions about this. So I am going to show you 2 examples, but please, please, please reach out for help if you need any more help. So what I'm going to do to graph this function is I'm going to make a table. Now, this is the way I do it. So if you reach out to, say, the tutorial center for help, they might explain it a different way, which is fine. I just want you to know that not everybody explains it the way I do. Okay, so what I'm going to do is I'm going to pick a few numbers, let's say 3, that fit what I call rule number 1. This is rule number 1 up here. And then we're going to have rule number 2. So I'm going to pick some numbers that fit rule number 1. So those would be numbers that are less than 0. Let's say -3, -2, -1. And then I'm going to pick some numbers that fit rule number 2. Let's say 0, 1, and 2. Okay. All right. So notice that rule number 1 says take the number and multiply it by 3. So that's a pretty simple rule. Rule number 2 says take the number and add 2. That's also a very simple rule. It's a very different rule. Okay. All right. So what I get when I do that, I get a bunch of points. 3 times -3 is -9. 3 times -2 is -6. 3 times -1 is -3. And then as I wait for that -3 to appear, there it is. Sometimes there's a lag between my tablet and what you see. Now I go over to rule 2. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. All right, so let's go ahead and plot those points. But I am going to come back to this table to show you one more thing. All right, now first of all, right off the bat, I'm going to have trouble with that -3, -9. So let's go to -2, -6, which is way at the bottom of the screen. I've got to find a better grid than this one. -1, -3. Okay. Now we know that f of x equals 3x is a straight line, right? It fits the form mx plus b. Okay. So really, technically, all I need is 2 points. So we could go ahead and connect those points. And now let's go over to rule 2. All right, so my points for rule 2 were 0, 2, 1, 3, and 2, 4. And that gives me another straight line. Okay. There is one missing piece to this. This graph does not show me anything that's going on between -1 and 0. I mentioned a few minutes ago that x can be any real number. It doesn't have to be an integer like -3, -2, -1. So just this once, since it's the first time we're doing this, I'm going to pick a few more numbers. Let's say -0.5. I'm picking things that are between -1 and 0. And why not -0.1? Okay, so those fall into rule number 1. All right, so that's going to give me 3 times -0.5 is -1.5, and 3 times -0.1 is -0.3. So let's see where those points end up? Negative 0.5 comma negative 1.5 is right about here. And then, excuse me, negative 0.1 comma negative 0.3, that would be right about here, okay? All right, so you're gonna wanna listen carefully for the next few seconds because this is the concept that a lot of people have trouble with, okay? Notice that rule number 1 applies for x less than 0, all right? What does x less than 0 look like if you were to plot it on a number line? It's all negative numbers all the way up to, but not including 0. So I need to get as close as I possibly can to that point where x equals 0. So here is the Mitchell patented secret to figure out how to do this. Well, let me show you on the graph what it looks like, and then I'll tell you the secret, okay? So basically, you want to extend this line all the way up to the point where x is 0. So it looks like that's going to happen at 0, 0. We'll confirm that in a second. To make it crystal clear that the point 0, 0 is not on this graph, I'm going to put a big open circle at 0, 0. Okay. So in the future, here's how you can, and we call that point a hole, by the way. It does not technically belong to the graph, but it's just indicated so you can see how, how far up that line segment goes. All right. In calculus, we call this kind of situation a jump discontinuity. It's called a discontinuity because it's discontinuous. There's a break in the graph and it jumps. It jumps from the bottom line to the top line. All right, so in the future, here's how you can figure out the location of that hole. All right, so I'm going to write hole over here. The hole is always going to occur at the value of x that's shown here, which will not always be 0. All right. In fact, in the next example, it's going to be something else. Plug that number into the rule that it does not belong to. All right. So rule number 1 is for x less than 0. Rule number 2 is for x greater than or equal to 0. So 0 is the property of rule number 2. But to figure out the location of the hole, we're going to put it into rule number 1. And sure enough, when I put x equals 0 into rule number 1, I get 0 come out as my y coordinate. And so the location of the hole is 0, 0. All right. So this is the correct graph for this function. All right. So let's look at the next example, and I would really like you to pause the video after you see this next example and try this one. All right, so let's bring that up. Okay, the next example. Oh, there's actually another piece to this which we can do together. Says graph the function and then use the graph to determine the domain and range of the function. And this function is f of x equals 4x minus 4 if x is less than 2 and is equal to negative x plus 1 if x is greater than or equal to 2. So please pause the video and try to do the graph. All right, and then come back and compare notes, and we'll talk about how to find the domain and the range. All right, so hopefully you had a chance to try that. Let's go over it. So I'm going to make my table. I'm going to pick a few numbers for rule number 1. Why don't we go with -1, 0, and 1. And then I will pick a few numbers for rule number 2. Let's say 2, 3, and 4. All right, so rule number 1 takes a number, multiplies it by 4, and subtracts 4. Rule number 2 takes a number, flips it to the opposite, and then adds 1. All right, so when I put my rule 1 numbers in, I get 4 times -1 minus 4, which is -8. 4 times 0 minus 4 is -4. 4 times 1 minus 4 is 0. And then going to rule 2, -2 plus 1 is -1. -3 plus 1 is -2. -4 plus 1 is -3. All right, so before we go over to the graph, let's figure out where the hole is going to be. The hole is going to be at 2 because that's where rule 1 and rule 2 break apart. Which rule does 2 not belong to? It does not belong to rule 1. All right, so this is going to be the location of the hole. So we're going to do 4 times 1 minus 4, and when you put 2 in there, you get 8 minus 4, which is 4. All right. So now I'm probably going to have to flip back and forth to this screen a few times. I'm never going to remember all those points. All right. So just waiting for my screen to catch up here. La, la, la. There we go. All right. I was about to pause the recording. The first point I got was -1, -8, which again, this grid is not really good for that. So let's start with 0, -4, and then we go up to 1, 0. This is the rule 1 part of the graph. All right, so why don't we extend this all the way up to the hole, which we decided was at 2, 4. So that part of the graph is going to look like this. And then, waiting for the screen to catch up. Okay, rule 2, now I need to go back and look. Starts at 2, -1. And then continues up to 3, -2. So 2, -1, or continues down, I should say. 2, -1. Here it comes. I saw it move. 3, -2. There it is. 4, -3. Okay, so this part of the graph is going to go down like this. All right, so hopefully that looks like what you got. So now let's talk about the other part of this question. I don't want to go back to the presentation just to get that. It was asking me to find the domain and range from the graph, okay? So here's how I like to explain this. The domain is the set of all x values that are represented on this graph. So imagine taking the graph and squashing it all down onto the x-axis. So if you took this piece here and squashed it onto the x-axis, you would not hit this point, but you would hit every point to the left of that, going on and on and on that way. And then if you took this piece and squashed it onto the x-axis, now you would hit this point and you would hit every point to the right. Okay. So what I'm saying to you is that the domain of this function is all real numbers. Every x value is represented somewhere on this graph. Okay. And remember, how do we write all real numbers using interval notation? Like this, -infinity, comma, infinity. All right, so now let's talk about the range. I'll do the range in blue. Okay, so if we were to squash this piece onto the y-axis, so to get the range, imagine squashing it onto the y-axis like that. That would give me this point all the way down, and then forever and ever and ever. And then if I were to squash this piece here, okay, I would not hit this point, but I would hit every point below that, including all these other points that I already hit. Okay. So not all real numbers are in the range of this function, only real numbers that are less than 4. So one way to say the range of this function is y less than 4. They are going to ask you to write that using interval notation, and the way you write that using interval notation is -infinity, comma 4 with a parenthesis next to the 4 because the 4 is not included. All right. So again, if you have any trouble with piecewise functions, you know, some of the things that people have been doing, look for other videos on YouTube. Come to office hours. I love to see people in office hours. There's all sorts of ways to get help, right?